So this is the second part of my solutions for M1 June 2016, question 6. It's a moments question. First thing I look at, is it uniform, is it non-uniform? If it is non-uniform, are you given the centre of mass of the thing? And we're not. In fact, that's one of the things it's being asked to find. Okay, it gives us a bit of information here. It's 6 meters long. Okay, it's 6 meters long, and it's on two supports with, let's label A here and B here. It's on two supports, one being 0.5 meters from S. Okay, so from A, if we say S is there, let's mark it below because I might be marking a reaction force up there. And then there's another support which is 2 meters from B. Let's put that there. And that's support T. Right, it's non-uniform, so we don't know the centre of mass. We'll mark that on in a minute. It says when a block of mass M is placed at A, just mark that in, mg, then it is on the point of tilting about S. So it will tilt about S, there'll be some reaction force there, but if it's tilting about S, means there's no reaction at T. So there's no reaction there. So we know the mass of the rod is 30. Let's just mark the centre of mass here, 30 G. And we're given, well, we've been asked to find, but we're given the label for the centre of mass, which is D from A. So normally if you've got a tilting situation, it's a good idea to take moments about the reaction force. If we take moments about S, the only two forces we've got counteracting each other are this one, the 30G one, and this one, the mg one. Now, the distance from A here is 0.5. That distance there is 0.5. Okay, so the moment of this force, which is going anti-clockwise, will be mg times 0.5. Whereas the moment about this force is force times this distance. Now that distance there is whatever d is, take away 0.5. So we've got 30g times d minus 0.5. Okay, so let's leave that there. Well, I suppose we can cancel the g. It's tidied up a bit. G cancels. And we can double the whole thing. So we can say m equals to 60 d minus 0.5. Okay, right, now we're given some extra information about what happens when this mass is moved to B. So this mass is moved over here. So just draw that. Let's draw that in a separate diagram. Remember, the supports are in the same place. It's just the mass is being moved. So we've still got the support S here and the support T here. And we've now got, this is mg. The mass of the rod is 30g. And the centre of mass from A is D. This is 2 meters here. There will be a reaction here, but this time there's no reaction here because it's on the point of tilting about about T. So there's no reaction at S. So the only two forces again are this one and this one. So we can take moments about T. We've got this distance here is going to be, we don't know what it is, but we know this distance from here to here is 4. So that distance, that marked distance there is 4 minus D. Okay, so we have 30G times 4 minus D equals the moment of this force, which is 2 meters away. So it's force times perpendicular distance, so that's mg times 2. 4 there for some reason. Mg times 2. Okay, so again, let's tidy this up, and it looks like this might work out quite nicely. G is that, and let's divide through by 2 now. So we've got M equals to 15 times 4 minus D. So we can equate these two. We have 15 times 4 minus D is equal to 60 D minus 0.5. We can divide by 4. So 4 minus D is equal to, not divide by 15 I mean, which gives us 4 D minus 0.5. So that gives me 4D, 4 minus D is equal to 4D minus 2. So that gives me 5D equals to 6. So D equals to 1.2 meters. So that's our first part of the question, the value of D. Of course, it's easy to forget there's a second part here because we've basically done the problem now. Now we've found D. We have, let's make sure we get the right one, the value of M. We can use either of these expressions, right, to work out M. So I'm going to use this one, and it might be useful then to check with the other one. So M equals to 60 times 1.2 minus 0.5, which is 60 times 0.7, so that equals to 42 kilograms. Okay, so that's question 6 done. Okay, so question 7 is an I and J question, but with forces and resultant forces and whatnot. I'm going to do a little diagram, but I'm not going to use it to solve a problem. But I think it's sometimes useful to know what's going on here, and just so that we get the principles, so we can understand our method. So just bear with me here. I wouldn't do this to solve the problem, but hopefully it'll help us understand what's going on, and therefore help us if we had such a question in an exam. We've got resultant 2 forces. Let's call the resultant F. And we know we've got 2 forces adding together to give F, the resultant F of F1 and F2. Now we know that F1 is minus I plus 2J, so let's just draw that. I'm going to draw it minus I plus 2J. I've got some helpful squares here to get the picture. So minus I plus 2J, that's my force F1. 1 to the left and 2 up. Now, it doesn't tell us F2, but it tells us a direction for F2. So let's just put F2, because we're going to do a vector triangle here. F2, we're told, goes in the direction I plus J, so it's parallel to I plus J. So it's somewhere along, it's going in somewhere in this direction here. That's my F2. I might end up shortening this line or lengthening it in a moment, as you'll see. Now we're also told the resultant is in the direction I plus 3j. So that means the resultant is going up like this. Okay, so I really don't want this extra bit on here, we can see. So that's my scale diagram to do it. Now, I'm not suggesting we use that to solve our problem, but it should give us a little idea. It's going to be somewhere over between 2 and 3, what our final answer is. So we're not given F2, but we're given its direction. So let's just, one principle we need to understand is that if we times F1 by a scalar, let's call it M, then we get, so the direction by scalar, by some scalar M, we will get, oh, sorry, bear with me, F1 we actually know. I'm talking about F2, is in the direction I plus j. If we times that by some scalar, I plus j, then for some value of m, some scalar value of m, that will be the correct force. If we can find m, then we've got F2, which is what we've been asked for. Now we're also told the direction of F. As I said, it's in I plus 3j. Let's call that n times I plus, just arbitrarily chosen. I didn't want to choose x and y or a and b, but I could have chosen. But anyway, n is I plus 3j. Sorry, f is equal to n I plus 3j. But for some value of n. Now we know that this is true. Okay, so we can say that f equals F1 plus F2. Let's just move that down to where we want it. Okay, so then F, which is Ni plus 3j, is equal to F1, which is minus I plus 2j. That's that F1 there, plus F2, which is that Mi plus j. Okay, now it'd be useful to multiply this out and bring together. That's Ni plus 3nj for the left hand side. Let's bring on my I bits together. If I look at my I bit there, I've got minus 1 at m, so that's m minus 1 times I. And if I'm looking at my j bit, I've got 2 and again 1m. So I've got 2 plus m equals to j. Now, if these two are equal to each other, so if they're equal, the I bits and the j bits have got to be equal. So equating the I bit, we've got n is equal to m minus 1. And we've got, equating the j bit, 3n is equal to 2 plus m. Well, we can easily sub for n here. So we have 3, could just put the n in there, 3 times m minus 1 is equal to 2 plus m. So 3m minus 3 is equal to 2 plus m. So that gives me 2m is equal to 5, m equals 2.5. Okay, which does seem to tie with what I saw here. 2.5 across and 2.5 up. Don't forget the question did ask us actually what F2 was, so it's no good just to give us the value of the scalar. So that gives us F2 is equal to 2.5i plus 2.5j. Okay, so that's the first part done. Okay, so that's a little bit problematic. The second bit is actually much easier, and it's just we've got a constant acceleration and we're using v is equal to u plus at because it wants the speed when t equals to 3. So if we call v when t equals to 3 is equal to u, which is the initial velocity, which is 3I minus 22j, plus 3 times 3I plus 9j. So I'm using v equals u plus at there. Putting that together, that's 3 plus 9, so that's 12i, and minus 22 plus 27, so that's plus 5j. But we want the speed, and the speed is the magnitude of the velocity. So the speed when t equals to 3 is equal to the magnitude of the velocity when t equals to 3, which is just using Pythagoras on those, and it's a 5, 12, 13 triangle, so the answer is 13 meters per second. Okay, much easier in the first part, I think. So, okay, let's move on to the final question. Well, it looks like a pretty standard connected particles question for a final question. No real angles to deal with. I often think it's quite nice to do these type of questions. First thing is, it's going to be accelerating clearly in this direction. Can't go any other way, obviously. And let's just mark on some forces. That's 3g, that's t. Because it says the pulley is smooth, we're going to have t tension the same throughout the string. We're going to use this part later in part B, by the way, but we're actually considering, we're going to apply F equals ma to both particles. This is 1.5g, weight 1.5g, and it's a reaction force which is obviously evenly balanced. And there's a frictional force. And we're told the coefficient of friction is 1/5. So we can easily say that the frictional force here is equal to 1/5 of r. And we also know that r, because if we're looking at particle P, we also know that r equals to 1.5g because it's just as forces are balanced vertically. So that means that F is equal to 1/5 of 1.5g, which is equal to 0.3g. So let's apply F equals ma to two particles now, because we know what F is now, it's 0.3g. So we've got, if we're looking at particle P, we've got the tension force, taking it upwards, taking it in that direction, T. And I always apply it in the direction that it's going. It's travelling in this direction, so T is positive. So T, take away the frictional force, which is 0.3g, is equal to the mass, which is 1.5 A. Okay. So then we can do, that's for P. And then we're going to apply F equals ma for Q. Well, we've only got these two forces here. We've got the 3g downwards and the T upwards, and that equals to 3A. So we're asked for the tension in the string here. Often with these questions we're asked for the acceleration and the tension. So it might be just as well to double the top one above. We've got 2t minus 0.6g is equal to 3a, and then we can equate these two. So we can sub for 3a, because we don't need t here, but really we don't need to worry about how we do this. It's not going to be hard work, I don't think. 2t minus 0.6g is equal to 3g minus t. So that gives me 3t is equal to 1.8 is equal to 2.4g. Nope, 3.6g, sorry. 3t is equal to 3.6g, so t is equal to 1.2g. We can leave it like that, or we can give 2 or 3 significant figures, so we're also allowed to give 11.8 newtons or 12 newtons as our final answer, but 1.2g is actually accepted here. Okay, so that's a 10-cylinder string. That was a nice question, really. Didn't ask for accelerator. I would imagine what a lot of people did, because we tend to do these things kind of routinely in the same fashion. We might have worked out A by adding these two equations together, worked out what A was by eliminating t and going back to it. Doesn't really matter, but anyway, there we go, not hard. Okay, so now it says the force on the pulley, the magnitude of the force on the pulley. Well, let's look at the force on the pulley now. We now know that t is equal to 1.2g. Let's call it 11.8 because that's the, we need to use, they say use 9.8 as a value for d. So 9 times 1.2 gets you 11.76. So 11.76 newtons and 11.76 newtons here. So we want the magnitude of the resultant force going in this direction, the combination of these two. And it also wants the direction, and the direction is obvious, it's 45 degrees below the horizontal, because we can see that the kind of triangle we have here. Below horizontal. Now looking at this triangle here, looking at this triangle here, we've got a very straightforward right angle triangle. We can call this resultant force F, say. So F, let's go back to blue. F is equal to the resultant of these two, which we can use Pythagoras' theorem, 11.76 squared plus 11.76 squared equals to 16.6 newtons to 3 significant figures, or 17 newtons to 2. It is, by the way, also equal to the square root of 2 times this, as you might see, because of course we can see that this is square root of 2 times by the magnitude of this. So you can give the exact if you want. The exact is 6g square root of 2 over 5, which is basically, if we wrote that as 6g over 5 times that by the square root of 2, because of Pythagoras' theorem, on a 45-degree triangle or trig or whatever, the exact value is that. So we've got 16.6, or this, or possibly 17 newtons to 2 significant figures. So that's it. That's June 2016 now complete. I hope you found this useful. Thank you. Bye.